Hi, welcome to the Calculus 1 lecture series. We are in the unit number 1, the topics. We are starting to introduce the derivative concept. But before that, we need to understand some limits concept. So the unit number 1, we covers the limits and the derivatives. And this is our lecture number 3. And in this lecture, we're going to talk about is calculating the limits by using the limit law. And in these sections, in this lecture notes, we're going to cover 3 topics. So the first topic is the limit law. So we're going to introduce several laws about the limits. And then we're going to take a look, specifically for the rational functions. So how about if when you substitute the value into the rational function and make the denominator equal to 0, how do we find the limits for that? Then the last topics here we're going to talk about is the squeeze theories here. This is a kind of like we have 3 topics. So I'm also going to divide this lecture to 2 videos here. Okay, so let's go ahead and get a start. Okay, let me go to our lecture notes here. Okay, so the first things we're going to talk about is the basic law of limits here. So the first law here, okay. So the first law is we're telling you here, right? So the number 1 here. So if you have a function, is there rational functions? Okay, and then A is the value is in the domain of F. So if you know the limits of the X approach to A, the F of X would be very easy. Would just be you substitute the A with the, substitute the X with the A's here. But of course, be very careful. The condition is that whatever the A you try to approach to has to be under the domains, right? So if it's inside the domain, you can just go, kind of just replace it, just substitute your X with A. Okay, so then, so the next loss here, and is like the sum of the limits, right? The limits of a sum is the sum of the limit. Okay, so of course, like we said, the sum is just another way say the differences here, right? Because the differences here is just you add a negative value. So basically it's telling you here is limit when you X approach to A, and then this is F of X plus minus GX is here. This will just be equal to the limit X approach to A, F of X plus minus limit X approach to A, GX here. That's what it means here. Then the next one here is if you have a limit X approach to A. So if you have a constant, if you C times F of X, so like here, C is the constants, right? So if you times the constants, then this one will tell us, hey, I can take the constant to the front. Doesn't matter, the constant. So you just take the limit to the F of X, and then you times the constants. Then the next ones here, they will tell you the product here. So if the here, this is F of X times GX, right? So if you multiply the 2 functions, and then you times it, and then here, so this will be the limit X approach to A, F of X times the limit approach to A, f of x and gx here. So the same ideas here is limit x approach to a. So if you divide by two functions here, right? So that means it will tell you this will be the limit x approach to a, f of x, limit x approach to a, gx here. Of course here, so that means we said provided the limit x approach to a, the gx cannot equal to zeros, right? So if it's equal to 0, I cannot have that in the denominator. Okay, so now the next things here, it will be the limit x approach to a. So if you have a function, you take the exponent's power, that means the exponents. So this will be the same. You take the limit x approach to a, f of x first, then you take the, then you take the nth powers here. So the same ways here, you can say, oh, okay, so limit x approach to a, and if I have the x to the nth roots here, let's put it here, so not just x is in general. Okay, so if you have the f of x to the nth roots, so what you here, that means you can do the limit, so you can put the nth roots in the outside, and here this is x approach to a, f of x. Of course, in order for this to work, we say this ones here has to be what? Has to be greater than or equal to 0 when the n is evens, right? We said it's even roots, right? So that's why, okay? And then the other things we already kind of introduced that is, if we have a constant here, so if you said x approach to a, so you have a constant. So what is it? This limit equal to? This limit equal to c, right? Because it's nothing to do with the x value anymore. It's just a constant function, so it doesn't matter, right? So it's a c here. Okay, let's take a look at the problems here. Okay, so the first one here we want to know is true or false here. Okay, so let's take a look here. So we said the limit x approach to a, f of x is equal to the infinity, and the limit x approach to a, gx equal to infinity. Then can we say the limit x approach to a, f of x minus gx equal to 0? Is infinity minus infinity equal to 0? No, right? So this one is a false here because I don't know. So infinity minus infinity, we don't know what is that because the infinity, like maybe one infinity run faster than the other one. Okay, so we don't know, and this is the situation we're going to take a look. How do we handle if we have a Low's indeterminate form of the limit? One of them is infinity minus infinity. How about for the same province, if I change the province to here, is this will be true? See here, so limit x approach to a, f of x plus gx equal to infinity. Now, this is true? Yes, this one is true, right? So this is true. So if I do this, this is true because I know the infinity at infinity still will be infinity. So the only thing we don't know is infinity minus infinity, right? Okay, so then the next one's here, let's take a look here. Said limit you times two function will be limit you take the limit first and then times is true or false. Hey, it's one of the limit law, so it's true, see here. Okay, so now this is limit x approach to a, f of the gx is equal to limit f of x and the limit gx this is true or false. This is what? This is a false here because we know what are those type of, this is a composed, right? So this is a composed function. Composed function, so this will be equal to limit. So this one's here, the correct answer. Okay, so let's put it here, the correct way to write it. So what is the correct way to write it will be the f of x. So it will be f of then the limit x approach to a, g to the x here. Okay. All right, so this is false here. Okay, so be very careful here because this is a composed function. You cannot separate as your times two functions here. Okay, now the part D is here. So let's say if f of x less than gx for every x and both limit x approach to a exist, can we say the limit f of x less than limit gx? It looks like kind of truth, right? But this is not. Okay, so this is false. The reason why it's false, let me give you contradictions for these things here. Like I try to find one example doesn't work. Okay, so now let's see here, right? So let's say here we have f of x is equal to negative x squared. Okay, and okay, so then the gx is here, it will be, let me give here, so this is x squared, so x is not equal to 0, is 1, x is equal to 0, right? So if you compare these two functions here, right, so f of x is negative x squared, gx is x squared when x is not equal to 0 is 1, when x is equal to 0. So I know for these functions here, f of x is what? If you just compare, f of x is always negative, right? Because it's negative x squared. So I know this condition satisfies f of x is less than gx. Okay, but now let's take a look at what happened to the limit x approach to a. So let's let a equal to 0. So we said a equal to 0. So when the x approach to a, what is my f of x going to approach to? Is negative to the 0 to the square. So it's 0 here. Now what is my gx going to approach to when x approach to 0? What is the gx going to approach to when x approach to 0, right? So here, because this is x not equal to 0, so you approach from left-hand side here, right-hand side here. So what is this one approach to? Is approach to 0 also. So it turns out that the limit f of x is equal to the limit gx, so it's not less than. So that's why this is what? This is a false here, right? So as we know, if I can find an example that's not satisfy, then I'll be able to do that too. Okay, so I will say that it's true. That means it has to be true for every conditions here. Okay, now let's take a look at, wow, this one's here is a rational function. We have some, we have the fractions here. So let's take a look. Let's say f of x to the 3 from the what? This is 3 from the what? Right-hand side, right? Now, what is the limit? Well, okay, so 3, I know that these functions, right? So this function, the domains here, right? So the domains here, is the x cannot equal to what? 1, right? And x has to be what? Greater than equal to the negative 4 here, correct? Because so that's what be the domains here, right? So this is the domain for this function. Then here they say x approach to 3 from the right-hand side. So I know, oh, the x approach to 3 from the right-hand side, this is what? This is inside of the domain, see here? Yes, this is inside the domains, right? If this is inside the domain, Then by our limit law, number one, see here, we say, hey, if it's a functions, it's the A is in the domain, then when you approach to A, it will just be equal to you plug the A into your function. So here, this is the same here, right? So I say, okay, now I know. So it will just be equal to, I plug the 3. So this is a 3 minus 1, then 2 to the 3 square plus what? Plus 3 plus 4. Okay, so this is a 2. This is 18 plus square root of what? Square root of the 7th, right? So the limit exists here. All right. Okay, so now let's take a look at problem number 3 here. Let's try to practice here. Oh, this functions here. This is the, what do we call it? This is the greatest integer function. That means, whatever the values inside there, you find the largest integer lessness, right? So if you still remember in your pre-cal, so the greatest integer function, so if I have a 1.999, right? So I'm looking for the largest integer less than this number. What is that? It's ones, right? So the same way is here, if you have like a 1.00001. So what is this numbers here? The largest integer less than this number still is 1 here, okay? So now let's take a look here. So for here, this is the limit x approach to 4 and x plus 1/2. 4 is inside the domains, right? So this one will be what? Will be equal to 4 plus 1/2, correct? And what is 4 plus 1/2 is 4 point what? It's 4.5 here. So what is the greatest, the whole number less than 4.5? It's 4, right? It's good. All right. So now let's take a look here. The next one here is that find the limit x approach to 3, okay, for the f of x. And in here, this is the piecewise function. And the way I break it 3 here. So for these problems here, so how do we do that? We say, okay, remember from the previous lectures here, we said the limit, if a limit exists, so we need to go through the left-hand side limit and the right-hand side limit, right? So let's take a look at x approach to 3. All right, so let's from the right-hand side here. Okay, so this is f of x. So what means the right-hand side? So that means that this is greater than 3, correct? So which function, which piecewise function I need to use if it's greater than 3? It's the second one, right? So this will be 3 to the square, so it's 9. So the same things here, I say, okay, now the limit x approach to 3 from the left-hand side, right? Okay, so what does the left-hand side mean? The left-hand side means less than 3. So which piece is less than 3? It's the first piece, right? So this will be 6 times 3 minus 4. So what is here is 14. Oh, wow. So I find that my left-hand side limit is 9. 14. The right-hand side limit is 9. So they are not equal to each other. So from the previous lecture, we say if limit exists, the right-hand side has to be equal to the left-hand side. So right now, the left-hand side is not equal to the right-hand side. What is our conclusion here? We say, hey, the limit x approach to 3, f of x, what? Do not exist, right? Okay, so now next things here, let's take a look at this ones here. Let's take a look for the graphs. This is the f of x. So let's say, hey, this is f of x graph, and this is a gx graph. We want to find the limits f of x f plus g to the x, we know by the limit law, this will be equal to what? You add two functions, so it's 2, the f of x plus limit x approach to 2, gx, right? Okay, so now let's take a look here, right? So remember we did it before. Okay, so like in here, 2 is here, right? 2 is here. So when x approach to 2 from the right-hand side, that means you go dun, 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 you go here, right? So you go to approach to here. From the left-hand side, you go dun, 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 approach to here. So doesn't matter is from right-hand side or left-hand side. What is this one approach to? This one approach to once, right? Because you know, when you go to the right-hand side, you go through your functions, right? So you go dun, dun, dun here, dun, dun, dun here. Doesn't have to be. So this 3, this is what? This is the value is f of what? F of the 3s, right? So, but the limit we say the approach is it doesn't have to be equal to the function of the values here. Okay, so now let's take a look the g functions here. Okay, so g approach to 2, so g is approach to dun, 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 go here, right? And the g approach to 2 from left-hand side is here. So what do they approach to? They both are going to approach to what? Approach to 3s here, correct? Okay, so now what is my final answers here? So final answer is 4, right? So that's why be careful by using the graphs here. The limit doesn't have to equal to the function values if this one is not defined in here, right? And then, you know, we're going to the next lecture, we're going to talk about how about if they are equal, what that means here. All right, so let's take a look at the next things here. Now we said the division by the 0, that's the rational functions here, right? So how about, you know, when I try to do the limit, then if I put the limit approach to the denominator, then the denominator turns out to be 0. So we know we cannot have a 0 in the fraction. So if you see this situation, how do we handle that? Okay, so we have 3 methods here. So first one is here, let's say cancel, right? Okay, so we can do cancel something by factoring both denominator and numerator. So if they have some common term, then we can cancel that. So maybe we can cancel the 0 out, okay? And then the second thing is here, maybe we can manipulate these fractions here. So okay, so we call this fraction manipulations here. Then the other things here, we say, well, maybe let's try to rationalize and expressions here. We're going to take a look at the example of all these 3s here, all right? And then we're going to stop the, so we probably going to stop after we do the first problem number 6, then we're going to do the remaining in our next videos here. Okay, so let's take a look here. So now let's take a look. We said the x approach to 1. Oh boy, I see here, I have a fraction. 1 is not in the domain of these functions here. So if you put the 1 in here, so if you substitute the 1, what you have here is 1 minus 1, and this is 1 square minus 6 plus 5. So what do you have here? You have 0 over 0. Oh, is this equal to 1? No. right? Okay, so be careful. This is not equal to 1 because it's indeterminate. We don't know what is 0 over 0. So we say, okay, we are in trouble right now. I have a 0 over 0 and the denominator equal to 0. So we say, what can we do? So let's take a look at our methods here. Say, hey, how about let's try to factor to see can simplify some things here. So let's say here is the x minus 1. Okay, so what is the x squared minus 6x plus 5? I can x minus 1, I can factor like x minus 1 and x minus 5, right? Okay, now after factor, so you will see here, oh, this is pretty good. X minus 1, x minus 1 cancel out. And then this one's here, this is x approach to 1. Then this is x minus 5. So now x equal to 1 is inside this domain, right? So it will just be 1 minus 5. You substitute to whatever your functions is. So this will be 1 minus 5 is equal to -4. Okay. All right. Okay, so let's take a look again. The second one is here. Okay, so you always substitute the value in first to see what you have here. So x equal to 6, okay? So you say here, I have 36 minus 6 minus 30. I just substitute x equal to 6. Then this is 2 times 6 minus 12. Oh boy, what I have here, 12 minus 12 is 0. 36 minus 6 minus 30 is what? Is 0. Whoa, I have this 0 over 0 again. So I don't know. So what we can do is here, oh, I have trouble with 0 again. So what is the first method they tell us? Hey, they said, hey, try to factor to see if factoring going to help or not. All right, let's take a look. Maybe we can get lucky for that. So this is a 2 x minus, so if you factor 2 out, is 6, right? Okay, now x squared minus x minus 30. What is this one? You factor, well, this is x minus 6, x what? Plus 5. Whoa, very good. So I see here the x minus 6, x minus 6. All right, so what I have here, so I have a limit x approach to 6 to the x plus 5. So what is the answer? 2 to the 11th here. Okay, all right. Okay, so now let's take a break here. And in our next lecture, we will continue to do the remaining part. All right, okay. And that's it. And looking forward to talk to you in our part 2 of this lecture series here. Okay.